Hi, everyone. I see we have a few people already sitting, waiting. We'll just give it a few minutes for everybody to trickle in before we get started. Welcome, everyone. We'll just give it one more minute and then we'll get started. Okay, I think we'll get started. Welcome, everyone, to our first in our year-long series of masterclass webinars celebrating and supporting the International Year of Quantum. And today on World Quantum Day, we're delighted to be presenting our webinar on visualizing quantum concepts, a cheat sheet for getting up to speed quickly. So today we're going to demystify the most important concepts in quantum computing and set you all up for continuing your quantum journey. First, a couple of introductions. So with me, we have Claire Edmonds. Claire is a senior scientist in the quantum computing research team here at Q-CTRL, where she finds ways to make the quantum devices we have today work more reliably. During her PhD, she was one of the first employees at Q-CTRL and has recently rejoined us after a postdoctoral fellowship at the University of Innsbruck. She has a particular expertise in trapped ion quantum computers. Throughout her career, she has been a passionate advocate for science outreach and education, helping to make quantum physics relevant and meaningful to diverse audiences. Welcome, Claire. And me, hi, I'm a staff product manager at Q-CTRL. I look after Black Opal, our quantum edtech product that we're going to find all about today. I've been with Q-CTRL for over 5 years, where I've been exclusively focused on making quantum computing more engaging and accessible for everyone. I'm not a quantum physicist. My background is in product management and communication in science and technology fields, having previously worked at the CSIRO, Australia's National Science Agency, and for Wired magazine. Okay, so we'll get a brief background on Q-CTRL and Black Opal. We are a quantum technology company. We've been around since 2017, and we have employees throughout Australia, the US, Europe, and the UK. And we make AI-powered quantum infrastructure software to make quantum useful. We do that with a couple of our key products. We have FireOpal, which is for quantum application developers looking to boost performance on today's cloud access quantum computers. through Boulder Opal, our product for professional teams working directly with quantum hardware, and Black Opal, which is one of the key reasons we're here today. It's our quantum edtech platform, and it's the product that I'm responsible for. And Black Opal enables anyone to learn quantum computing in a really practical, visual, interactive, engaging way with no prerequisites at all. We also have Ironstone Opal, which is our quantum navigation technology that works in situations where GPS is not available and which outperforms conventional GPS alternatives by up to 50 times, achieving true quantum advantage in navigation. This is a massive achievement that we announced less than 24 hours ago. So you can find more information about this on our site afterwards for those that are interested. But all of our award-winning products are used by tens of thousands of users worldwide. And actually, in terms of Black Opal, last week we won the EdTech Breakthrough Award for the second year in a row, something we're really proud of. So with Black Opal, we want to make quantum accessible to everyone. And that's why we're excited to be an official partner of the International Year of Quantum, a global initiative that aims to raise public awareness of the importance and impact of quantum science and its applications on all aspects of life, and to help anyone, anywhere learn more about quantum. So to that end, welcome to the world's largest quantum computing class. Welcome to this, the first in our year-long series of webinar masterclasses planned throughout the year. More on the rest of our masterclasses at the end, but for now, let's get started with today's webinar, Visualizing Quantum Concepts, a cheat sheet for getting up to speed quickly. We're going to give you a fantastic grounding in the key things you need to know about quantum computing to get started in this field. You'll leave today with a new intuition about what makes quantum different, why that's useful, and we'll point you in the right direction for where you can go next to continue your quantum journey. I will say up front, we'll be going through a question and answer at the end of the webinar, so be sure to enter your questions using the Q&A feature at the bottom of the screen. And okay, with that, I'll hand over to Claire.
Great. Thank you so much, Mick. And thank you all for joining me here today. I've got the absolute pleasure of starting our webinar series this year. And honestly, I think I get the most exciting topic to talk about, which is just quantum fundamentals, because there's nothing we can do without these basic principles of quantum mechanics. And I hope to give you a little insight into why quantum physics is different from classical physics today, and give you some of the tools that can help set you up to start working on quantum algorithms, start exploring the Black Opal platform, start using real quantum computers on the cloud. And so with that, I'm going to start with a slightly different topic, which is not quantum, but rather classical computing, because I think you need to understand the history of where we're coming at to understand why quantum computing is so interesting, but also not particularly scary. Like, quantum computing gets a bit of a bad rap sometimes, I think. I think people think it's really hard or scary or unapproachable or magical. But realistically, all quantum computing is doing what we've been doing for hundreds of years, which is just building computers. What we've been really good at as a species of people is we develop some sort of knowledge, some sort of intuition about physics or mathematics. And the second we come even close to understanding it, we start using it. We start building machines out of it, and we start building computers that we can utilize to solve problems. So, I mean, take thousands of years ago, once we understood geometry and mechanics, we were building really simple little computing devices like abacuses. Once we invented the mechanical gear, those devices got a lot more complicated. We started building adding and subtracting machines, which were just analog versions of today's computers. I believe it's Lord Kelvin's Fourier analysis machine, which can predict the tides. We started building more complex machines like astronomical clocks. These could predict the positions of the planets and the stars and calculate movable holidays that would depend on the cycle of the moon, and were very important in the Middle Ages. And many of these can still be found in operation today. Even the simple slide rule shown here in the middle of the screen is a very simple analog computer, and was still being used really up until the 1970s in the classroom as a pocket calculator. All of these devices are computers. They all take some input information, they process it in some predetermined way, and they get an output, which is hopefully the answer to your question. These are all analog computers. They're built on continuous mechanics, not discrete, and they're all built to solve specific problems. Then in the 20th century, we took a big step. We mastered electricity, transistors and circuits, and we did the same thing. We used that knowledge to build today's digital electrical computers, which are reprogrammable, which means that they can solve many types of problems. We call these classical computers, the sort of computer that you're probably sitting on, the computer that I'm sitting on, and they can be described entirely by classical physics, the sort of physics that you encounter every day. And now we're just taking another step. Throughout the 20th century and throughout the 21st century, we've been mastering our understanding of quantum physics. And we've seen that there's new possibilities here. If we can harness this physics, we can build a new type of computer, one which is going to solve a new type of problem. So with that, let's take a step down into the quantum world, because this is the world that we don't see every day. Quantum physics has, as I say, this reputation of being very unapproachable. Einstein coined it spooky. In reality, quantum physics is just unintuitive. It's because you can't see it every day. You can't witness it at work. If you take something like the field of gravity, it's a very, very complicated theory. But we all feel like gravity is much more approachable than quantum mechanics because we could go outside and throw a ball and you'll have a good idea of where it will land. You can see this force and this field of physics at work. But you can't split an atom in your kitchen. You can't witness superposition with your cat. And that's because if you want to see quantum effects, you're going to need to make an object quantum. And to get an object to be quantum, it needs to be very small, very cold, and very isolated. Anytime something tries to interact, to talk to our little quantum object, it becomes a bit less quantum, a little bit more classical. So with that, I want to talk about some of the things that we use to witness quantum mechanics in the real world and the things that we're using to build up our quantum computers. It might be charged ions sitting in a vacuum chamber with as many of the surrounding atoms and molecules removed. We can hold these atoms in position and we can cool them down to near absolute zero temperature using lasers. And this is my specialty, so if you have any questions, feel free to ask. Smaller still, we could go down to an electron, a tiny little spin suspended on the material of a semiconductor and controlled by electrically charged pieces of metal. We can use special superconducting circuits where we actually use the electrical properties of the circuit to encode our quantum information in what we call an artificial atom. It's acting just like that atom in the vacuum chamber, but is written in electricity. You could also use something like a photon of light, tiny and very antisocial. Photons don't like to interact with all that much. So these are all the building blocks that we can use to actually build a quantum computer and start to witness some of the quantum effects that we're going to talk about today. Today, I want to talk about three major properties of quantum physics: superposition, measurement, and entanglement. These are the three things which makes the quantum world so different from the classical world. So let's start with the one which I think most people have encountered through the story of Schrodinger's cat. And this is the idea of superposition. In the classical world, objects are in a fixed state. Now, I'm going to be using that word quite a lot today, state. It's a relatively abstract word. All that means is it's some property of the system. It might be its position. It might be its electrical charge. It might be its momentum. All that matters is that a state is something which you can use to describe an object, and hopefully you can manipulate, you can change something's state. So in the classical world, objects are in a fixed state. A coin is either heads or tails when it sits on the table. A dice will show just one number. Even when you flip a coin, once it's in the air, you have a 50% chance of getting heads or tails. But once it lands, it is definitely in one of those two states. It's either in heads or it's in tails. In quantum physics, even after the coin toss, your coin can exist simultaneously in heads and tails. And that crucial word is and, not or, not either, but and. In mathematical terms, we call this a probability distribution. We have some probability of finding the coin in heads and some probability of finding it in tails. The relative probability, the relative chance of finding in those two will depend on how you make the superposition of heads and tails. Now, it's not just the object's heads or tails that can be in superposition, it could be its location. Rather than the coin sitting exactly on the table in one spot, it could have its position start to smear out. It's simultaneously located both here and there. But we'll never see this with a coin. It's too big. It's not small, cold, and isolated. But insanely, at the microscopic level, the world of atoms and electrons and photons, this is really happening. An object can exist in a delocalized state with no fixed position, no fixed state, but spread out over multiple possibilities. In quantum computing, we usually think about superposition occurring between different energy levels. So in our atom, we have these electrons orbiting around, and we can move them from a ground state into an excited state. And we can do this by just injecting a bit of light or heat, some sort of energy to excite our atom from the ground to the excited state. And this is what we're going to create our superposition over, two different energy levels that we can move in between. We can smear our quantum object out between the two of them. And that object can stay in superposition, spread out over simultaneous different possibilities until we look at it and check where it is. But more on that later. So how do we actually represent one of these superposition states? Well, in classical computing, the information carrier is called a bit. It's a two-level system that can either be written as a 0 or 1. This is how we store all information in classical computers and how we do all our information processing. It all happens in the bits. But we know in classical computing it's discrete. We can only have a 0 or a 1, nothing in between. In a quantum state, we can have something called a quantum bit or a qubit. This is where we have a superposition between two different levels. We can call them again 0 and 1 to make it an analogy to a classical bit. But instead of being only able to be in the 0 state and only able to be in the 1 state, we can actually have any superposition between these two states. And we represent this mathematically using this notation here on the left of the screen called ket notation. These little symbols here, the little arrow type symbols are called kets. And we can visualize it using something called the block sphere, which you see here on the right hand of the screen. So what are we looking at here? Well, this little term here on the left, is called the wave function. This is our quantum state. And that's going to tell us everything there is about our quantum object. Now, we have a quantum state that can have two positions. It can be a 0 or a 1 because it's a quantum bit. And so we've got some amount of our superposition in the 0 state and some amount of our position in the 1 state. And these two little numbers in front, the alpha and the beta, are just telling us how much chance there is of finding it in 0 or 1. Is it going to be 50-50? Is it going to be completely random? Or is it going to be 99% in 0 and just 1% in 1? On the block sphere, this would look like having a state all the way up here near the North Pole, nearly entirely in the 0 state. Whereas if you drew a state on the equator, you'd have an equal 50% superposition of 0 and 1. So some of the possible states you can have look like this. This is how we write them out, that we can get a 50% 0 and 1 state. Here I've got another 50% 0 and 1 state. These are both 50% in the two states, but you'll notice something else differs between them, and that's called the phase. And the difference between these two things is the difference between being on the right-hand side of the block sphere, here, or being at the front of the block sphere. It's just another degree of freedom that we get in quantum mechanics. We get 2 degrees of freedom. We get how much 0 and how much 1 there is, and the relative phase between these two terms, which spins us around the block sphere. We can also just be in the state 1 at the South Pole. That is a perfectly valid quantum state, but it can also be described classically because it is just purely in the 1 state. So I think a really natural question at this point is, quantum mechanics is such an interesting thing, but why don't we see it every day? Why don't we see it in big objects? And to answer that, I think we need to understand what it means to measure something in quantum physics. And so that brings us to our next big topic of measurements. Coming back to our quantum coin, we've flipped it, it's had a spin, and now it's landed. And we're going to say it's in a 50% superposition of heads and tails. How do we know which one it's going to be in when we look? Well, we have a look, we look in, we bring in our microscope, and we find out that actually the coin was in heads. We could go again, and we could find that it was in tails. It's a very strange idea that it was in this superposition, and suddenly look, and we collapse the superposition. We make it probabilistically fall into one of the two options. Another way of looking at this is looking at the Bloch sphere. When it's on the south or the north pole, our quantum state is completely classical. It's just 0 or 1. And when we're looking, it can only ever be in 0 or 1. But when we look away, we can start to get a quantum state. We can start to slip off the north pole and start to evolve around the Bloch sphere into all of these quantum states until the second we look again. But what does it mean to measure something? Does it mean that you need a giant eye in the sky? Do you need to get out a microscope or a magnifying glass? What does this actually mean fundamentally? Well, when we measure something, we need to talk to it. We need to interact with it. And this interaction needs to be able to distinguish between the different states in the superposition. It needs to somehow have a different interaction if the quantum state is in the 0 compared to if it is in the 1. This might mean that we send in a perfectly tuned pulse of light to check where something is. We might capture a photon to determine which path it took in a maze. We might send in an electrical pulse for a spin qubit or a microwave tone for a superconducting qubit. The important thing is that whatever we send into our system to probe it, to measure it, has to interact with the system, and it has to be able to discriminate between the different states. It might excite our quantum atom. It could absorb our quantum photon. And once that interaction has happened, we've not just learned which state of the superposition our quantum object is in, but that measurement, that interaction has actually caused the superposition to collapse into that state with some probability, some random chance. So let's take a real example of trapped ions. In trapped ions, what you do is you send in a laser pulse. And now, if you have some superposition state and you shine your laser and it collapses it into the ground state, what you'll find is that your ion stays dark. Nothing happens. You don't see anything. But instead, if you've got a superposition and your laser pulse causes it to fall into the excited state, your ion will glow. We call this state-dependent fluorescence. Depending on which state the superposition collapses into, we either see fluorescence or none. And that's how we know we're either in the 1 or in the 0 state. And now something I want to mention, because I think this is a really big confusing point, is that it doesn't need to be a scientist who sends into the light, who sends the laser light in. It could be a gust of wind that knocks over the laser. It could be light from a distant star coming in at just the right time to disturb our quantum system. There doesn't need to be any consciousness here in the measurement. All that matters is that the interaction happens, the physical interaction. Doesn't matter who or what makes it occur. It doesn't even matter if anyone's around to find out the result of the measurement. That information might get lost. The act of measuring by itself will destroy the quantum state. And after that measurement, we'll be left with something that can be described purely by classical physics, a classical object. And that's why we don't see big objects act quantum mechanically. They're just interacting with too much all the time. They never get the chance to become quantum mechanical. This is why when we build a quantum computer, we need to use building blocks that are really small, really cold, and really isolated, so that they don't interact with anything outside our control, and they only talk to what we let them talk to. So at this point in the webinar, we've seen two of the three big building blocks to understand quantum mechanics. We know that a quantum object can be in a superposition of multiple states at the same time. And we know that a measurement can destroy that superposition, causing it to randomly collapse into one of the physical classical states. But now we need to understand the most spooky part of quantum physics, the thing that had even Einstein worried, and that's entanglement. When we've been talking about all the previous topics, we've been talking about a single object, a single block sphere. It might be an atom or a photon, which can be put into superposition and then measured. But throughout this whole process, we can describe the object just by itself. We don't need information about anything else to describe the state of the object, the superposition, or its classical state after measurement. We can describe all of this using just a single object. When you have two objects that are entangled, they can no longer be described as single objects. They become intrinsically linked, and you need to talk about the quantum system as a whole. Information about their quantum states becomes correlated, fundamentally tied to one another. You can't represent a entangled state by a block sphere because it's got too many dimensions as well. It's a four-dimensional system when you have two qubits, and a block sphere can only show two. So to start off, let's talk about correlations, because entanglement is all about correlations. But correlations aren't necessarily a quantum thing. Classical objects can be correlated. And what I mean by that is that the result of one thing can be exactly the same as the result of the other thing. If you know you've got pairs of socks that are red and green and blue, and you pair them together always perfectly, and you pull out one sock pair at random, and you look at one of them and you see it's red, well, then you know the other sock that you haven't looked at is also red. Those two things are correlated, but they're not entangled and they're not quantum mechanical. We can flip two coins when we've stuck them together rigidly with a piece of metal, such that they always flip together, and they'll always either land on heads and heads or tails and tails. You can never see heads and tails simultaneously because you've tied the coins together. The outcome of those two coins is perfectly correlated. To get entanglement, you need to introduce a new thing to the correlation, and that's superposition. We're coming back to topic number one again. Not only can two quantum objects be perfectly correlated, their quantum states always matching exactly, but they can also be in a superposition of perfectly correlated states. Take my two quantum coins here on the screen. We've got them in a superposition of two possible correlated states. So here on the left, there is some chance of finding both coins in the heads and the heads. Here on the right, we've got some chance of finding them both in tails and tails, and they are simultaneously in both of those possibilities. You'll notice that each state in the superposition involves both coins. You can't separate out the states of the two coins and write them independently. Take the first state. The left coin is represented by the left entry, heads, and the right coin is represented by the right entry, also heads. This state is telling us there is some likelihood of finding both coins in heads. The other state in the superposition says there's some likelihood of finding both coins in tails, but there is no chance of ever finding them in heads and tails or tails and heads. And then the really amazing thing that happens with entanglement is because you're in this correlated superposition, you actually only need to measure one of the objects to collapse the superposition. Because when you collapse the superposition for one object, you have to collapse it for the other. Let's consider me and Mick. I'm going to entangle together two atoms in my lab, and then I'm going to send one over a fiber. I'm going to give it to Mick in another room. Now, we're going to have our atoms, and we know that I prepared them in the state where they were both in 0 and both in 1. And Mick's going to have a look. He's going to get out his laser and check what state his atom's in. And he's going to find it's in the 1 state. And again, he's made that happen by looking at it, by measuring it. It's collapsed from this superposition to a single classical state. But we both know I didn't make any chance of him measuring a 1 and me measuring a 0. That was impossible, which means that I must have a 1. That's the only outcome, we were either going to both get a 0 or both get a 1 after the measurement. And the scary thing about this is that Mick measures his. He sees it's a 1 and instantly knows I've got a 1. Instantly knows that my superposition has collapsed. And that sounds like faster than speed of light knowledge. And that's what got Einstein really worried about this. Turns out there are a few sort of philosophical subtleties, which means that we don't need to be too scared about this faster than light information because he doesn't know what I've done to my atom in the meantime. But nonetheless, his act of measurement has instantly caused mine to collapse its superposition. So there's 3 takeaways I want you to think about when it comes to entanglement. The first is that if you want to entangle 2 objects, you need to bring them close enough together to share information because they need to get linked. They need to interact with each other in a controlled way such they learn about each other's quantum states and become entangled. The second thing is that once they've been linked, once they've been entangled, you can separate them and you can send them the distance of the universe apart. And the third thing is that measurement on only one of those objects can cause both objects' superposition to collapse. That is spooky action at a distance. The reason we care about entanglement is that, firstly, it is actually present at the microscopic level. So we want to understand what's happening in our universe. We need to understand entanglement. And secondly, it enables larger computations because the more states that we can put into our superposition, the more computational size we have, the more possible interference patterns we have, and the larger representable states that we can make in our quantum computer. So our computers get exponentially bigger. So now we've talked about these 3 ingredients, 3 fundamental principles of quantum mechanics. Superposition, which really is just the absolute most important topic in my opinion, but I'm sure you'll find some who disagree. Measurement and entanglement. It actually turns out that once you've got a pretty good grasp of these 3 concepts, nearly everything else in quantum mechanics and quantum computation follows. You can start working towards quantum technologies like sensing, like we've already heard about, atomic clocks, or really precise imaging, like MRI imaging. It's all based on quantum mechanics. You can start looking at simulations of chemical molecules or materials, like building a better solar cell. And then you can finally, once you build a big enough device, you can start thinking about algorithms and computation, optimization and logistics, as well as things like cryptography, which we know is one of these big pinnacles that we're working towards in quantum computation. So with that, I'd like to jump into question time if anyone's got any questions. I hope I've been able to shed a little bit of light on these 3 topics, and I hope you understand a little bit more about the quantum world than you did before we started. Thank you very, very much.
Thanks, Claire. Thanks for that fantastic introduction to quantum computing and showcasing the power and clearing up the mystery of superposition and measurement and entanglement. I hope it's left you with a clear understanding of what makes quantum computing different and exciting. So yeah, we will now move on to our Q&A. So I encourage you all to ask any burning quantum questions by using the Q&A feature, just at the bottom there, and I'll type those through in a second. But whilst we're waiting for you to type those, I'll just highlight a couple of things. So we have our upcoming webinars on the screen here. So the next one coming up will be Flipped Learning in May. We'll show how Black Opal can be a key part of quantum in the classroom with the Flipped Learning model, featuring our CSO, Michael Hush. In August, we'll look at quantum applications. So looking at the state of the art in terms of quantum applications showing promise in industries such as finance, cybersecurity, and more, featuring our head of quantum computing research, Yuval Baum. And then in November, we'll look at careers in quantum. We'll take a look at the rapid growth of our field and the diverse range of skill sets and opportunities available to those interested in joining the workforce. That'll feature our talent manager, Seb, who's responsible for bringing in the fabulous expert team we have at Q-CTRL. And there's even more yet to be announced, so mark those in your calendar. Okay, so I see there's a couple of questions in here, so we'll get onto those. So I think just we can go next slide there, Claire. Okay, so the first one we have here is for Claire. This is from Rob. Um, so, he asks, how does the entanglement connect to qubits? So they can be far away in space from each other, but somehow they're entangled. So yeah, maybe just a bit of clarification on entanglement there, Claire.
Yeah, absolutely. I mean, I'm not going to be able to give you a satisfying answer, I'm afraid, because this is one of the big open questions in quantum mechanics. How do we get this instantaneous collapse of two quantum states? And there've actually been experiments which have proved that the collapse happens faster than the speed of light, because people have managed to entangle two particles and then send them apart on optical fibers by hundreds and hundreds of kilometers, and then do really fast measurements that beats the speed of light. We don't know is the answer. This is what got Einstein so upset. And there's one theory which is called the theory of hidden variables, which is essentially disproven, which is that there's some secret other thing that we can't measure, which actually is already determining the way, like before the two particles get separated, they say to each other, let's always fall in 0, 0. And so when they get separated, they don't actually communicate. They already know before they get separated. But we've proven that this doesn't happen. I mean, I've heard sort of incredible theories about, well, maybe there's another dimension of space-time where there's actually some physical link, some sort of pipeline that connects the two of them, and we're just seeing the entry into our dimension. I mean, the ideas are endless, but we actually just don't know how it works. It's just something that we've observed and we know it happens, and so we're just trying to utilize it as best. But there's a lot of research going on to exactly how this entanglement works.
Fantastic. Thanks, Claire. I can see that we have a couple of questions about where to go next after this sort of introductory talk. So I can probably handle that one and give a little bit of advice here. So obviously, I'm a little bit biased. A genuinely useful next step is to complete the full Black Opal course. Perhaps some of you already have. If so, congratulations and fantastic. But it is a really great way to build on the fundamentals that you've learned today, to go a bit deeper and to go a bit further in terms of building circuits, understanding some of the key algorithms, starting to learn how to program a quantum computer. And I did see there was also a question about looking at some domain-specific aspects of quantum computing. And actually, we'll be looking at adding some new modules to Black Opal over the course of this year, looking into some of those key domains. We'll be focusing initially on optimization and logistics and really diving into what are those problems and how can you approach it with a quantum computer and get some useful results even today. So those will be coming up. Hopefully they answer some of those questions. But in terms of where else you can go next, I mean, I think after Black Opal, you're very much in a great position to choose your own adventure. You can build on the fundamentals to go deep on coding for quantum computers if that's what you're interested in, learning a language such as Qiskit or working towards something like developer certification. But also recommend keeping an eye on some of the hackathons and things that come up throughout the year. They're a great way to learn with others, especially those that, for example, IBM or QBraid put on. They're fantastic. We put on some as well throughout the year. Equally, Black Opal is a really good foundation for further learning at a university level, if that's something that you'd like to do next. Really great way to assess your own sort of keenness and have a really great springboard for going much deeper in a more formal setting. Lastly, I'll say Black Opal alone will even get you to a point where you can look to make a move into the quantum industry. Quantum companies like Q-CTRL, we need people of all sorts of professional backgrounds that understand quantum, but aren't necessarily quantum physicists like me. For example, I've been here for 5 years. So a lot more on that in our Quantum Careers webinar later in the year. Okay. Let's have a look at what else we have here. Okay, so I've got one here. Perhaps one for you here, Claire, which is we mentioned quite a few different ways that we can build quantum computers, like with trapped ions, semiconductors, superconductors. Which types of quantum computing are most commonly used and show the most promise?
Right, yeah. And actually that ties quite nicely into another question I can see asking about which type of qubit has the longest decoherence time and what's being done to increase these times. So yeah, there's a lot of different platforms which you can use to build a quantum computer. They all have different advantages. Something like photons is really promising for quantum communication because photons are really easy to transmit. Trapped ions and superconducting qubits are pretty much stuck where you've got them in your experiment. So you'll always need to transmit that information to photons to exchange it. In terms of superconducting qubits, trapped ions, spin qubits, which are increasingly sort of coming up now, and also like color centers in nanodiamonds, they've all got different advantages. So I might get this wrong and I'm going to get in trouble. I think trapped ions have, in general, the longest coherence times. But that's not the whole story because what really matters is how much computation you can do in that time. So what matters is how fast your gates are relative to how long you've got, how long your coherence time is. So superconducting qubits tend to have faster gates than trapped ions, but trapped ions have more time to do them in. So it kind of balances out. From the point of view of what's being done to improve these coherence times, I mean, that's really quite exciting because okay, there's some work happening on the materials development. If you're building superconducting or spin qubits, it's all about how you actually build these devices. In trapped ions, it's usually more about how we can shield these devices from the environment to make sure no stray magnetic fields come in, that there's no elevators moving or trucks coming by or trains, because these are actually the things that cause decoherence. But in addition to that, you can do things at the software level, and that's what we're doing at Q-CTRL. So we have tools such as something called dynamical decoupling, which is targeted to improve your coherence times, both for storing information, but also within an algorithm. If you really cleverly work out how to tune your dynamical decoupling, you can make your algorithm go for much longer by extending out your coherence time and your memory. That work? Can't quite see. I think is that everything that the question was asking. But yeah, lots of different advantages. Superconducting qubits are scaling quite well, but trapped ions are also looking really promising. It's anyone's game, so to speak.
Thanks, Claire. I think there was a few questions in there about decoherence that you've covered off there as well. I'll ask this one here. So I keep hearing that quantum computers will have a significant impact on cybersecurity. Is that really true? And what will be the impact? I think there's been a few questions there about cybersecurity.
Yeah, the interesting thing about cybersecurity was it was the first real quantum computational algorithm that somebody wrote in the 90s that showed that quantum computers could do something that classical computers can't or faster. Yeah, so in quantum mechanics, we can absolutely break RSA encryption. We're a long way away from doing it, I need to stress, because the sorts of devices that you need to break modern standards need to be millions and millions of qubits, and we're at sort of like more like 1,000. But yes, there is a quantum algorithm which can factor really large numbers into their prime factors, and that's the basis of RSA encryption. The qualifier here is that we are moving off RSA encryption. We are increasingly inventing quantum proof forms of encryption. So it's something which has to be happening now because a lot of information is stored encrypted. And if it gets snatched now with a weak encryption, it can be broken in years to come. So you find that the US government has employed their government lab called NIST, the Lab of Standards and Technologies, to invent or to find a new series, a set of quantum proof cryptography protocols. And they've put those out recently and people are moving across into that. So it's not going to be a giant quantum collapse in 10 years when someone gets the first quantum computer and everything's going to go crazy. But absolutely, the standards that we have been using up until today are vulnerable to quantum computing in the future.
Excellent. Thank you, Claire. And I think we have one here. Here we go. Okay, so I think this answers this gets to a couple of questions. I might ask them both, and perhaps they're related. So, one is why can't we fully harness the power of quantum computing today? What are the limitations or hurdles we still need to overcome? And I think that's somewhat related to another question here from Vishal, which is long shot, but can we ever achieve qubits with decoherence times in months or years?
Yeah. Depends on the decoherence. So there are different types of decoherence. One is, so if you think of that Bloch sphere, the first type of decoherence is how long you can stay in the excited state before you decay down to the ground state. And the other is how stably can you keep this equatorial phase. The first type, probably we can find really stable states that don't want to decay. We have them today that can absolutely last for days, maybe. It's very hard to make those measurements, of course, certainly hours. I think it's probably unrealistic to ever expect that we'll have coherence times of that length, but we don't need them. That's the point, because we're never going to use a quantum computer to store information. We've got classical computers and classical memories for that. So quantum computers will only ever be used to do the quantum cores of algorithms. Even in really big, like logistic algorithms, you might find that you give a lot of the computation to the classical computer, and then when it just gets that one job in the algorithm where the quantum computer is better, you swap over from your CPU to your QPU, you do that, and then you come back. So I think quantum computers are just going to be a very targeted tool. So we're never going to need those sorts of coherence times for them. And then, sorry, Mick, what was and the first question was about,
I guess the challenges that we still need to overcome in terms of useful, quantum computing and some of the applications that we are looking at.
yeah. So it all comes down to noise and scaling. Our quantum operations are pretty poor when you compare them to a classical computer, which might make a mistake 1 in 1 trillion operations, whereas we tend to get mistakes in 1 in 1,000. And there's this really sort of inconvenient thing about quantum computing, which is that the way that the algorithms work means that errors build up. It's not just like on every gate, you either got an error or you didn't, and you can check and you go, oh, we had an error, throw it out, try again. Your errors build up with some probability because it's almost like the errors come into the superposition. And if you ever want to check if there's been an error, you risk collapsing your quantum computation. So that's where something like quantum error correction comes in. It's a way of probing your computation throughout the algorithm without destroying the quantum state, but finding out if there's been a certain type of error and either just discarding the data or correcting it if you've got a powerful enough code. Noise is really tough, magnetic field noise, electrical noise, better manufacturing, and also what Q-CTRL is doing. So we do have our hardware team who's working on those amazing sensors that you heard about. But the software team, which I work on, we're just taking the devices that we've got today. We're getting access, we're not improving the manufacturing, and we're saying, well, how can we push those fidelities up, particularly at the algorithmic level, by doing better compiling, better gate design, adding dynamical decoupling, all of these things that can be done at the software level can really improve the accuracies of your quantum circuits today.
Fantastic. Thank you, Claire. Okay, well, I think that's probably it for today. If you can go to the next slide, please, Claire. We hope we've whet your appetite to learn even more about quantum computing. If you aren't a Black Opal subscriber yet, it's the ideal way to build on what you've learned today. So many of the lovely visuals that Claire used came from Black Opal. I think it's a really accessible, visual, interactive way to learn quantum computing. And we are running a limited offer during the next couple of weeks with a 25% off lifetime access for Black Opal. So you can scan the QR code. You can also go to qcontrol.com/black-opal. But also we'll send a follow-up email with the details. So don't worry, you won't miss out. And we'll also include a recording of the webinar in that email as well. So with that, thanks to our senior scientist, Claire Evans, for our fantastic presentation today. And thank you all for joining the webinar. Be sure to stay tuned for the next one in late May, Flipped Learning, How to Deliver Black Opal to Any Kind of Classroom. and we'll have more to announce on various other webinars throughout the year as well. So until then, all the best on your learning journey with quantum computing, and I hope to see you all in Black Opal soon. Thanks again, and we'll see you in the next one.